Hello, I'm Charlotte Lyddon, a lecturer in coastal dynamics at the University of Liverpool, and today I will be talking to this virtual workshop about coastal resilience and hazard mitigation. Coastal and estuarine regions are where climate change, human development, and natural variability intersect. They are dynamic systems, highly productive, and home to a large and growing proportion of the world's population. But they are also increasingly exposed to erosion, flooding, and compound coastal hazards. Coastal and estuarine flooding is one of the most immediate and damaging hazards. It arises from the interaction of tides, storm surge, waves, river discharge, and sea level rise. Coastal flooding occurs when an extreme sea and/or river level exceeds a local threshold, for example, a sea defence, that results in inundation. It represents the most dangerous and costly impact facing estuaries and coasts, and the second highest hazard to civil emergency in the UK. The highest is pandemic influenza. Globally, it has caused more than 3 million deaths since 1700, and in the UK, it causes in excess of £540 million in annual damages. Coastal and estuarine flooding is increasingly a result of compound events rather than single processes. Compound flooding is driven by extreme sea levels and river discharge occurring at the same time or in close succession. Two drivers which are not extreme on their own combine to amplify the impacts. The combined drivers can exceed a threshold and cause flooding. The video shows progression of pressure and rainfall as a storm passes over the UK, which could cause compound flooding as a drop in pressure increases sea level and rainfall causes an increase in river discharge. The plot on the right shows total water level in black and river discharge in blue, with a short lag time occurring close together. The hydrograph in blue can be used to describe a river flood event in more detail based on width, steepness, and magnitude. And resilience is a term with many definitions, so it's important to be clear what we mean here. At its broadest, coastal and estuarine resilience refers to the ability of societies, communities, and ecosystems to cope with, recover from, and adapt to hazards, and where possible to mitigate impacts by reducing exposure and vulnerability. But here I focus on a more specific, foundational component of resilience. In the context of coastal and estuarine flooding, resilience is about building the knowledge needed to anticipate flooding, rather than simply responding after impacts occur. This requires accounting for the complexity and interdependence of flooding drivers, particularly interactions between marine and fluvial processes, to identify critical system sensitivities. So in that sense, resilience here is not just about adaptation measures such as defences or planning controls, but about using scientific understanding to inform mitigation and adaptation strategies that remain robust under uncertainty. Critically, this also means planning for flooding that exceeds historical experience, as climate change and sea level rise push systems beyond observed conditions. This definition sets up the pathway I'll show next, linking coastal and estuarine flooding science directly to resilience outcomes. It starts with sustained observations of water levels, waves, river flows, and inundation across coasts and estuaries. These data are critical for identifying flooding drivers, extremes, thresholds, and compound river events. That observational foundation supports process understanding and numerical modelling. By combining hydrodynamic models with sea level rise and climate projections, we can explore how flood frequency, depth, and extent may change, and where uncertainty matters most for decision making. And flood hazards only become risks when they intersect with people, infrastructure, and ecosystems. So translating flood science into resilience therefore requires engagement with stakeholders and communities to ensure that risk and impact assessment reflect local exposure, vulnerability, and tolerance to flooding. The outcome is evidence-based flood adaptation and planning, informing design levels, early warning systems, land use planning, and nature-based solutions that support broader societal and ecosystem resilience. My research sits at the foundation of this pathway, developing the process understanding and predictive capability that enable coastal and estuarine flood resilience in practice. If resilience is about accounting for complexity and interdependence, understanding flooding drivers and planning beyond historical experience, then we need methods that can identify where systems are sensitive and when flooding is likely to occur. The work I'll focus on now does exactly that. It uses historic records of flooding combined with instrumental and model data to identify site-specific thresholds for flooding in UK estuaries. These thresholds identify when and where compound flooding occurs, providing the hazard information to guide mitigation to reduce impacts. So, to identify site-specific thresholds for coastal and estuarine flooding, the first question we need to ask is whether historic floods have actually been documented in sufficient detail. Polygons of flood extent, which include information on start and end date and basic information on the source of flooding, are available for Wales and England from national agencies. Incidents of flooding are taken from the lower estuary, shown here in a box for the Conway in North Wales. And we're going to look at a couple of these in more detail. So overall, 12 flooding events are recorded in the lower estuary. 6 have river and sea level data available on those dates. So once we have records of flood extent, the next step is to understand the hydrological and marine conditions that produce those impacts. For each recorded flood event, we link observed inundation to river discharge and coastal water level time series. This allows us to examine the relative contribution and timing of fluvial and marine drivers and to assess whether flooding occurred under extreme single drivers or compound conditions. The lag time here is nearly 6 hours. The river discharge in blue reaches a modest peak, but sea level is high. This event corresponds to a much smaller flood extent polygon located in the upper estuary. What we see is a short lag time between peak river discharge and elevated coastal water levels, indicating a strongly compound event. Although neither driver is necessarily the most extreme in isolation, their coincidence is sufficient to exceed local flooding thresholds in the upper estuary. This is supported by observational evidence. Here's a photograph and a news article documenting flooding at this location, which helps validate the timing and extent inferred from the gauge data. We have 6 records of flooding when gauge data is available, showing river discharge here on the x-axis and sea level on the y-axis. These 6 recorded events are shown as stars. The black square is astronomic tide, so the vertical black line indicates the magnitude of storm surge, and colour indicates lag time. We see a range of river discharge, but all are occurring on higher sea levels. The key limitation of using historic records of flooding is that not all flooding events have been documented, and there are gaps in this record. There can't just be 6 times when flooding happened in the Conway estuary. So we add on the top 50 most extreme river discharges on record and their paired sea level. And then we also identify the top 50 extreme sea level events in the historic tide gauge measurements at this estuary and cross-checked these against online sources, online news, reports and academic literature to see if these events also led to flooding. So we see the 6 recorded events and then many more incidences of flooding emerge. A more comprehensive historic record of flooding allows a more accurate threshold of flooding to be set in the estuary. An interpretation of where we might set a threshold for flooding, the conditions above which cause flooding, is shown by this dashed blue line. But can we set a more accurate threshold for flooding rather than me just drawing a dashed line in PowerPoint? We then used web scraping to analyse which of these additional top 100 events do and do not cause flooding. The date was entered into 4 different search engines and results were tagged based on what the news or reports tell us about event drivers. But there are still some gaps. There are events where we know flooding happened, but there are no records because they happened pre-internet. And the middle space in this plot shows similar conditions causing flooding or not. So we want to fill in these gaps in our knowledge of what conditions actually lead to flooding. To move beyond historic observations and develop predictive capability, we use process-based numerical modelling to explore coastal and estuarine flooding hazards. In this case, we use the Caesar list flood model, which is a two-dimensional diffusive wave model to simulate flooding in the Conway estuary. The model is set up using a digital elevation model interpolated to a 20-metre grid and includes flood defence heights to represent existing infrastructure. We first ran the model over a 12-month period to simulate water levels and flood extent, validating the results against pressure sensors and gauged observations within the estuary. Building on this, we designed a set of idealized simulations to systematically test the relative influence of key flooding drivers: water level, storm surge, river discharge, and the timing between them. Here I show one of these scenarios, each consisting of 520 simulations. These combine 40 river discharge conditions with 13 incrementally increasing tidal levels alongside a representative storm surge. Each simulation runs for 72 hours, allowing for model spin-up, and peak water levels and peak discharge occur after around 40 hours. River discharge is represented using idealized hydrographs ranging from 25 to 1,000 cubic meters per second, and tides are based on an idealized M2 signal spanning neap to spring conditions, increasing in 25 centimeter increments. Storm surge is scaled to the maximum observed skew surge of 1.03 meters. This framework allows us to isolate sensitivities, identify thresholds, and directly examine how compound drivers interact to produce flooding. We use flood area to describe flooding from each scenario, a function of river, sea levels, surge magnitude, and time lag. A baseline threshold is calculated from a scenario representing moderate river flow conditions with water contained in the main channel, dry floodplains, and a water level high enough so that no midstream shoals emerge. The base case is drawn from an actual event of the 27th of January 2016 in which no inundation occurred. The flooded cell counts, the maximum area from the water depth output layer, are recorded in a matrix and subtracted from the baseline threshold. A cell is considered wet when the local water level exceeds a threshold of 2.5 centimetres. So this slide shows the results from scenario 1. The colour scale represents flood area relative to the baseline simulation, with red indicating an increase in flooded area. You can see that some combinations of river discharge and sea level in the bottom left do not produce flooding at all. The contours connect simulations with the same flooded area, and these provide insight into the dynamics of flooding across this parameter space. Changes in the contour gradient, shape, and spacing indicate how sensitive flood extent is to one driver relative to another. In this figure, we can identify different flooding regimes. Some scenarios are occurring when both drivers are elevated to a similar extreme degree. Some are dominated by extreme river discharge in the bottom right, others by extreme tidal water levels in the top left. Notably, convex contour shapes, such as those visible in the middle sections of the 3 and 4 kilometre square contour, indicate a compound flooding effect. In these regions, the combined influence of river discharge and sea level produces a disproportionately large increase in flood area, highlighting the importance of accounting for compound flooding processes. On this slide, the contours are superimposed on the web-scraped flood records, with the events where flooding was documented now highlighted in yellow. What we see is that these observed flooding events align with the regions of greatest sensitivity in the middle of the parameter space, where dominance shifts between marine and fluvial drivers. Using this approach, we define the flooding threshold in a simple, decision-relevant way, a yes-no outcome, indicating whether flooding occurs anywhere in the estuary under a given combination of drivers. But this raises an important question. What do we actually mean by a flooding threshold? In this context, a threshold is the point at which flooding begins to occur at specific locations, not just an increase in total flooded area across the estuary. To identify that, we need to move from estuary-wide metrics to individual grid cells. So here we move from estuary-wide thresholds to site-specific flood thresholds, showing the conditions under which flooding does or does not occur at individual locations. We have the Conway estuary as a whole on the left, and then we show the flood results for specific receptors. We have a primary school and farmland in the lower estuary, a railway in the middle estuary, and a dwelling in the upper estuary. These plots illustrate the codependent thresholds between river discharge and total water level at each location. In some cases, flooding is primarily controlled by a single driver, either discharge or sea level, meaning a single variable flood probability analysis may be sufficient. In contrast, locations in the middle estuary exhibit compound flooding. Here, flooding occurs across a much wider range of combined river discharge and sea level conditions, demonstrating that joint probability analysis is necessary when both drivers influence flood magnitude. So, have flood records been documented? Well, records are incomplete. We need to fill in the gaps with instrumental and model data. Can we establish thresholds for flooding? Yes, using both gauge and model data. We can explore flood dynamics and show sensitivities. We need to account for where compound flooding is occurring, which highlights the need for user-specific thresholds and joint probability assessments where both drivers influence the hazard. So coastal resilience is not about eliminating flooding, but about understanding when, where and how flooding occurs, and using that knowledge to reduce consequences for communities, infrastructure and ecosystems through targeted mitigation and adaptation. By explicitly accounting for compound coastal estuarine drivers, joint probability and system thresholds, this work shows how flood science can move decision-making from reactive responses to proactive, risk-informed planning. Resilience here means building the scientific capability to identify critical sensitivities, to anticipate flooding that exceeds historical experience, and to design mitigation and adaptation strategies that remain robust when tested against physically consistent future climate and sea level projections. In this sense, flooding science forms a foundational element of coastal resilience, supporting coastal systems and communities not only to withstand flooding, but to reduce impacts, adapt, and continue to function in a changing coastal environment. Thank you for listening. Please get in touch if you have any questions, and I look forward to the discussions.